Alright, this video is on electron affinity. It usually follows after the videos on ionization energy. So electron affinity can also be explained by talking about the effective nuclear charge. So an effective nuclear charge is how much of the nuclear charge from the center of the atom does the electrons in the outer shell, the valence shell, feel or experience. We've talked about that something like chlorine here. Chlorine has 17 protons in the nucleus, and it has 3 shells around it. And there's 8 electrons in the first shell, or 2 electrons in the first shell, 8 in the second, and 7 in the third. And that the effective nuclear charge the outer shell electrons receive from the nucleus approximates 17, the actual nuclear charge, minus the core electrons, which is 10 in this case. And this is what I mean by core, the inner shell electrons. So this is the valence shell. These are the core electrons. So 17 minus 10 gives us an effective nuclear charge of 7 positive. So because the outer shell sees an effective nuclear charge of 7 positive, it's possible for a chlorine atom in the gas phase to gain an electron and become an anion, a negatively charged ion. So let's talk about what the definition of electron affinity is. It's the amount of energy released when a single gaseous atom, or an atom in the gas phase, gains an electron. So in comparison to ionization energy, which is the amount of energy required to remove an electron from a single atom in the gas phase, electron affinity is how much energy is released when a single atom in the gas phase gains an electron. So we haven't talked about delta H in class yet, but let me just say, when we see a negative value for delta H, that means energy given off. So that's like we start at this energy and we end at this energy, and so the loss of energy given off, has a negative value. Think of it like this. This is at 4. This is at 1. So change would be 1 minus 4. Final minus initial. We get a negative 3. Now, electron affinities generally are given positive values. So electron affinity values, the more positive the value, the more energy given off. And again, do not confuse that with delta H. That's a different term. So we have electron affinity values and we have delta H values, or change in enthalpy values. So we're going to focus on the electron affinity values, not the delta H values. When we compare that to something like sodium, let's look at sodium. So sodium in the gas phase, a single atom of sodium in the gas phase, gains an electron and then becomes a sodium anion, not a positive ion, but an anion in the gas phase. So for sodium, the amount of energy that would be released, and let's keep it in parallel with delta H first. So delta H for the sodium ion would be a negative 52.9 kilojoules per mole. Alright, so hopefully you're starting to see the rest of the story here. Ionization energies are very low for metals, and electron affinity and ionization energies are very high for nonmetals. And electron affinities release lots of energy compared to the metals. So nonmetals tend to lose a lot of energy, release a lot of energy when they gain an electron. Metals, not so much, only negative 52 versus negative 349 for the chlorine. So now you're starting to see why Sodium forms a positive ion because it has low ionization energy compared to chlorine. And chlorine becomes a negative ion because it has a high ionization energy and it releases quite a bit of energy when it gains an electron. All right, so let's look at a table of electron affinity values. So electron affinity values as a whole, as the trend goes, it increases as you go across the periodic table. The amount of energy released increases as you go up across the periodic table, and it decreases as you go from top to bottom. Well, that makes sense. That's in line with effective nuclear charge, in that as we go across the periodic table, the effective nuclear charge increases, so that allows there's more of a nuclear charge on the outer shell of the atom as we go across, and it also decreases as we go down because we're adding more and more shells to the atom, and so the outer shell is getting further and further from the nucleus. So that's the trend. But if you start looking at the trend, you will see there are some anomalies. So the first anomaly you see is, hey, we don't see a release of energy here for beryllium. It's less than or equal to 0. We don't see a release of energy here for nitrogen. It's actually -7. That means it requires energy. And then the obvious, the last group, the noble gases, they're all negative except for maybe helium. So that's anomalies that we need to focus on. And then one other anomaly, not discussed in the book, but really important, is this anomaly here. So we know that electron affinity should decrease as you go from top to bottom, but here we actually see an increase in electron affinity. So again, just like we did with ionization energy, you may want to pause the video at this point and try to figure out why there are anomalies in groups 2 and 15, and then why is there an anomaly in group 17. I think 18 is pretty easy. I think you'll see why that's easy once you draw an orbital diagram. So again, I think the ones that are more difficult is 2, 15, and then 17. So pause the video, think about it, come up with your best explanation. All right, welcome back. Let's talk about beryllium. So beryllium has 2 electrons in the 2s orbital. All right, 2s orbital. It has no electrons in the 2p. So what we're saying here is beryllium in the gas phase is going to gain an electron and become a beryllium negative ion in the gas phase. So that means we're putting an electron up here in the 2p. Well, we know that the 2p is higher in energy than the 2s, so that costs us energy. It takes energy to get up into the higher energy level, or sublevel, if you want, higher sublevel, let's say that. And that this electron is going to create electron-electron repulsions. And we saw when we talked about ionization energy that the anomalies occur in groups 13 and 16. So now it's like you have an electron that would be like for boron, so it was easy to remove this electron from boron. So it's difficult to add the electron to beryllium and put it up in this higher sublevel. So that's why we generally see in group 2 an anomaly here of electron affinities being less than or equal to 0. Now, I bet you can figure out the nitrogen. Nitrogen, same thing, right? So it's nitrogen, it's 2s, and we have 2 electrons there, and then we look at the 2p in nitrogen, and we go 1, 2, 3. So that's what nitrogen looks like. It's in group 15, has 5 valence electrons, and there they are, 1, 2, 3, 4, 5. And now what you're trying to do is say nitrogen, monoatomic nitrogen in the gas phase gains an electron and becomes nitrogen negative ion in the gas phase. Where does that electron go? Well, it has to go right there. Now you're pairing two electrons in the p sublevel. So now you've got electron-electron repulsion within the p sublevel, and also electron-electron repulsion between the 2s and the 2p, and the 1s, if you want to think of that as well. So that's why nitrogen has a -7. It doesn't release energy, it actually requires energy to put electrons, or put an electron on nitrogen. Neon, even easier to explain. Neon, you have the 2s electrons, and then the 2p is full. So we go 1, 2, 3, Hund's rule, then go back and pair. So that's what neon looks like. So if you're going to add an electron to neon, it actually has to go up into a new energy level. It has to go up into the 3s. So that's a large amount of energy. And that's why it's -29. It actually costs quite a bit of energy to put the electron into a new, not a new sublevel, a new level. All right. So all the noble gases, they have a full outer shell, and you're going to have to put the electron into the next higher energy level. All right, last anomaly. Let's look at chlorine. So chlorine, you would expect it to have a lower electron affinity than fluorine, because as we go down, yes, they all have a Z effective of approximately 7 positive, and chlorine has 3 shells instead of 2 like fluorine, so you'd expect, since it's got an extra shell, less influence of the nucleus on the outer shell electrons. That's what we've been saying. But chlorine's actually higher. So what is it about chlorine that is so special? Because we do see it decrease from chlorine to bromine to iodine to astatine. So we do see the decrease. It's just chlorine that we see the anomaly. All right. Well, let's put that over here. So this is what chlorine looks like. It has 2 electrons in the 3s. It has 5 electrons in the 3p. So a total of 7 electrons. So it's got a place to gain one here. It's got a high Z effective. I ought to gain that one. But why is it greater than fluorine? What's so different about fluorine than chlorine? Well, the hint is think about period 2 versus period 3. What is the difference between those two periods? What is the difference in sublevels in period 2 versus period 3? So when n equals 2, my only L values are 0 and 1, and that's the S sublevel and the P sublevel. But when n equals 3, my L values are 0, 1, and 2. Remember, this 2 is the D sublevel. We haven't put any electrons in the D sublevel because we don't fill up the D sublevel until after we go through the 4s1 and the 4s2, and then we go into the 3D here. So because there's the unfilled 3D sublevel, chlorine can accept an electron more readily than fluorine that does not have the D sublevel. So an electron can, that even though it's accepting it here, because there's more space, so to speak, chlorine can accept that electron more readily. And so that's why we see a slightly larger increase in electron affinity value for chlorine versus fluorine. All right, so know the anomalies. Groups 2, Group 15, Group 18, and Group, chlorine in Group 17. All right, again, why do we call it a periodic table? Because as we go from left to right, top to bottom, we see a cyclical property. So here we go. We have lithium. Then we see a decrease in ionization energy for beryllium. We've talked about that anomaly. Then we see an increase up to carbon, which it should. And then we would expect it to increase all the way to fluorine. But We see another anomaly here for nitrogen, group 15. So we see anomalies in groups 2 and 15, and we've talked about those. Same thing here, group 2, group 15. Group, this one we can't quite see that, right? But that's what we're looking for. So again, looks similar in pattern, and again, as we go from chlorine to bromine to iodine, we do see a decrease in electron affinity, and that's because we're adding more shells to the atom. It just happens to be an anomaly here, though, between fluorine and chlorine. I mean, you can see it here too: sulfur, selenium, tellurium. All right. A couple things to note: units for electron affinity, kilojoules per mole. And again, we're applying that against atomic number, the number of protons in the nucleus. I hope that helps. I hope it helps explain why chlorine forms a negative ion versus sodium. Sodium forms a positive ion. So low ionization energies for sodium ions being formed, large releases of energy for chloride ions being formed. Remember, chloride is the ion form. So, and again, remember, positive ions are cations, negative ions are anions. I hope that helps. And the next video will be on comparing positive and negative ions, or positive ions in their neutral atom and negative ions in their neutral atom.